Here's the solution to problem number 2 from the quiz from unit 2.1. So this is a quiz on electrostatics, on electric potential. On the first problem, we applied this equation that says work is equal to the amount of charge that's moved multiplied by the potential difference that it's moved through. But we also know there's something known as the work kinetic energy theorem, right? So if this charge Q started from rest at point P, and there's an electric field due to all the charge of this ring, so there's some value of electric potential, we'll call it V naught, at this point P, and then there's a different value of electric potential at the center, we'll call that V. Taking the difference between those values, V minus V naught, gives us some value of delta V, and so whatever charge is released from rest here, if it's accelerated toward the origin, it gains kinetic energy, and that kinetic energy is the same thing as the work that was done by the electric field. So we can put these two together and say Q times the difference in electric potential is the work that produces the change in kinetic energy. Now it's at rest at this point, so delta K is the same thing as whatever final value of kinetic energy it has when it reaches the origin. Let's not confuse capital V with lowercase v. Just evaluate this. I think we're given enough information. We're given the mass of the particle, and we're told the speed that it has when it reaches the origin. So if we do 1/2 times 4 times 10 to the negative 10th times 3 times 10 to the 4th quantity squared, it gives us a kinetic energy of 0.18 joules. Okay. So actually then we could figure out what this difference in electric potential is, right? Let's replace work with the final kinetic energy that the charge develops. Then delta V is that kinetic energy divided by the charge that was moved through that potential difference. So the difference in electric potential between these 2 points is equal to 0.18 joules of work divided by 2 times 10 to the negative 6th coulombs. So this gives us a potential difference of 90,000 volts. Now the electric potential is not 0 at the origin, and it's certainly not 0 at this point. Unless otherwise stated, we assume that the electric potential is equal to 0 at a point infinitely far away. So in fact, how would we calculate the electric potential at the origin? Well, hopefully you know that that's just equal to K times the total charge distributed around this ring divided by the radius of the ring. How do we find the electric potential here? Without going through this full derivation, you should at least be able to remind yourself, find this in some previous notes. If you need to rederive it, it shouldn't be too difficult. The electric potential at this point is equal to K times Q divided by the square root of x squared plus r squared. In other words, just divided by r, lowercase r. Okay, so delta V must be the difference between these two values. So in other words, it's KQ times the quantity 1 over r minus 1 over the square root of x squared plus r squared. Well, this we can evaluate. We're given all of these values, right? The radius of the ring is 12 centimeters. X is 9 centimeters. So if we've got all of these values, then we can determine the value of this part of the expression, which comes out to be 1.67. So let's see, well, we know what K is. That's 9 times 10 to the 9th. We just found this delta V is 90,000, so we can now solve for the amount of charge that's on this ring. It's equal to 90,000 volts divided by 9 times 10 to the 9th and 1.67. So we get that the charge on the ring is 6 times 10 to the negative 6 coulombs, 6 microcoulombs. But that's not what we're asked for. We're not asked for the amount of charge, we're asked for the linear charge density, the value of lambda. So all that charge is spread out around a circle. Linear charge density is the amount of charge per length, although the length around the perimeter of a circle would be 2 pi r. So 6 times 10 to the negative 6 coulombs divided by 2 pi times 0.12 meters gives us 7.96 times 10 to the negative 6 coulombs per meter. And there you have it. Thanks for watching.